All right, everybody. So the problem of the day, there's a lot of talking. You guys are the polar opposite of my Chem 110 class this morning. They just sat there staring at me silently. All right, so let's calm down and try to get through these problem of the days. The key with these reactions is identifying your alpha position. So in this case, we've got an alpha position here, and we've got an alpha position here. So in this case, we can identify our substituents that are added on, and in this case, we've added on this substituent to the alpha position in the first example. And then in the second example, we've added on this substituent. So let's really quickly try to piece this together. And in each case, we're starting out with ethyl acetoacetate. But I don't want class to be distracting. So we'll react this with sodium ethoxide and form our enolate. And then in the second step, we're going to react this with our alkylating agent. And so you can alkylate in the alpha position. And then what do we need to do to get to our final product?
We need a
How do we convert? Acid and heat. So we need H3O plus, which will convert that ester into a carboxylic acid. And then if we add heat, we can do our decarboxylation. All right. One thing I did want to bring up, though, is this whole step. Do you think this alkylation step would go very smoothly? Yes. What's the problem with our electrophile here? Yeah, it's a very hindered electrophile. If you tried to do a backside attack on that, it wouldn't work well. So yields will be low. Nope. In this case, if we add heat, we're going to favor the elimination, right? Because our enolate is also a base. So in this case, our secondary electrophiles aren't preferred. This was actually a mistake in the Klein textbook, but I thought it was a good example of what not to do. Let's go to our next one. So again, we're going to start out with our ethyl acetoacetate. And we're going to react this with sodium ethoxide. And then I normally choose the bulkiest alkyl halide first. So which one of the groups should we choose? The one with the phenyl ring or the ethyl?
phenyl.
Yeah, the phenyl. So in this case, we would react it with benzyl bromide.
But does it make it wrong if you do it that way?
No, usually people prefer to get their bulkiest substituent on first, though.
Okay, but we haven't said that before. Now we know though.
Why do they prefer to do the bulky one first?
Because it has the more hindered attack. So the less bulky your nucleophile is, the easier it's going to be. All right, and then in the next one, we can do the same thing. We use sodium ethoxide. This time we use ethyl bromide.
If you don't do the bulkier one first, though, will that gas be affected?
No, I'll give you guys credit for it.
Thank you. But if we do it from now on, then that's enough.
It's just important to try to maximize your yields, really. All right, and then the last step, we want to get rid of our ester, so we can treat it with acid, convert it to the carboxylic acid, and then crank up the heat.
What if you did it without heat? What would happen? I did it, but I'm just wondering. Would it do anything?
You wouldn't get the decarboxylation occurring well. Whoop. And there we go. We've got our final product. That looks funny. I'll move this. There we go. That looks better. All right, so we do need to know how to do these reactions pretty quickly. You can go through and draw the full mechanism for these, but it draws on chemistry from previous chapters.
So will you, on the exam, you won't ask us to do the full mechanism?
I could. That would be fair game. Yeah,
But will you though?
I could. I might now.
Oh, please.
All right, so let's go back. Since we've had almost a week off from class, let's go back really quickly and briefly talk about conjugate addition reactions because we're going to continue on today. And so we said that conjugated alpha beta unsaturated ketones and aldehydes have unique reactivity. This is really similar to our alkene chapter where we talked about conjugated alkenes and their unique reactivity, specifically 1,4 versus 1,2 addition. And we said that it's a unique situation where we have two different electrophilic sites. So in this case, the example I gave you was that we can take, hey you guys, there's a lot of side conversations going on. We can take our aldehyde and do an aldol condensation and get to our alpha-beta unsaturated aldehyde. But if we treat it with a really, really strong nucleophile like a lithiate, we're going to get 1,2 addition. But if we treat it with a weaker nucleophile, we'll get 1,4 addition. We're going to continue on with this sort of chemistry today, but we're going to do a reaction called the Michael addition. And the Michael addition is a conjugate addition.
How come they didn't use his last name?
I don't know.
It's Michael.
Maybe it is.
Oh, that is
I actually haven't looked that up. Conjugate addition, where we use an enolate
I mean, it's a bear food problem.
as a nucleophile. And I'll show you guys what I mean with this example. I'm going to take this diketone, and if I treat it with sodium hydroxide, actually let me even space this out, Na plus and OH minus, followed by an alpha-beta unsaturated aldehyde, followed by acid, we can do what's called a Michael addition. But let's try to problem solve our way to the answer. All right, so what will the sodium hydroxide do?
Grab that beta proton in the middle of the two.
The alpha proton.
Alpha, I'm
Yeah.
sorry. Alpha, that's my name. I swear.
Okay, so we've got really acidic alpha protons, pKa of about 9 or 10. The hydroxide will grab that, dump down electrons, so we've got a highly stabilized enolate. And this enolate is referred to as your Michael donor. And this Michael donor will react with our Michael acceptor, which is in step 2. Oh. And the Michael donor will specifically attack the beta position because it's a conjugate addition reaction. And it will clamp down and kick up electrons onto that oxygen. So we have our enolate. And then in the last step, we're going to react this with acid. So we're not going to form our enol. Instead, what will happen is this will clamp down The pi bond will jump up and grab that. And we end up back to an aldehyde. So this is the idea of a Michael addition reaction. Instead of having another nucleophile like a lithiate or a cuprate attack our aldehyde that's alpha beta unsaturated, we're actually using an enolate as our nucleophile. And one other thing I really wanted to bring attention to is that with a Michael donor, is that it must be a highly stabilized enolate. Otherwise, 1,2 addition will occur. So because it's a highly stabilized enolate, it makes it less nucleophilic, so weaker nucleophiles like to do 1,4 addition, not 1,2 addition. So Michael addition reactions are usually in between two carbonyl groups or next to a really, really strongly electron withdrawing group. So let's take a look at some common Michael donors. Yeah.
You said weaker nucleophiles like to do 1,2 additions.
Sorry, weaker nucleophiles like to do 1,4 addition. I might have misspoke. Strong nucleophiles will add directly into the carbonyl. Weaker nucleophiles will do the conjugate addition and attack in the beta position. Yep. All right, so now let's determine what Michael donors are most common, because there's usually a handful that you'll see. So a really, really common one, like I said, is in between two carbonyl groups. So you can have a negative charge there. Alternatively, instead of a ketone, you could have esters that you could hydrolyze off into the acid or even decarboxylate. So these are both very common. Or you could use your ethyl acetoacetate enolate like we saw in our problem of the day. These are all highly stabilized because they're in between two carbonyl groups. The other ones that are pretty common is to have an enolate next to a cyano group. Why is that highly stabilized?
Because it's between, no, I know.
So the top three are stabilized due to resonance induction, right? So if we've got a cyano group on there, that's very, very electron withdrawing. That helps stabilize that negative charge on your enolate. The next one that's also along those same lines is we can actually do this with positions adjacent to a nitro group. And then the other example I said that will work are lithium dialkyl cuprates. All of these are highly stabilized and will attack the beta position. So really, a Michael addition is simply referring to a conjugate addition where it's an enolate or some sort of nucleophile adding into the beta position. All right, so now let's take a look at something a little bit different. What if we don't use a highly stabilized enolate? So let's take a look at this example. I'm just going to use cyclohexane hexanone. First step, I'm going to react this with LDA, which is a strong base. We need a really strong base in this case because the alpha proton is significantly less acidic. And then in the second step, we're going to react it with an alpha beta unsaturated aldehyde. And then in the third step, we're going to treat it with acid. So the question is, when we deprotonate it and form our enolate, is it going to attack, let me actually use my highlighter, at the beta position, or is it going to attack at the position directly on the carbonyl? Yeah, this time, because it's a very, very unstable enolate, it will actually attack the carbonyl carbon. And so if we were to draw out
Really?
our product that we would get from this, this would be our major product. And our Michael addition would be our minor product. So the reason behind this is that unstable enolates can and will attack your carbonyl.
How come we have been doing it this whole time? It's so stupid learning.
So if we look back up at our examples up here, specifically let's go back to our example problem. The enolate that we had in that bottom left-hand corner is highly stabilized. It's in between two carbonyls, so it's stabilized through resonance. That makes it less nucleophilic, which favors 1,4 addition. But if we go down here, if we were to form an enolate from cyclohexanone, we would have an enolate that's only stabilized across one carbonyl group, not two, which makes it much, much more reactive and a stronger nucleophile.
I think we did both problems that we're talking about that.
Yep, we're going to go through a few problems that are really similar to these Michael addition reactions. So the question is, if we want to form the minor product, how can we do that? So in order to get actually, let's say conjugate addition, i.e. beta position attack, we must use a weaker nucleophile. So the question is, how can we turn this ketone into an enolate that's a relatively weaker enolate? And there's a really clever trick for this. And again, this was another named reaction. We're throwing down a lot of named reactions. And so the solution is referred to as the Stork-enamine synthesis.
Oh, this is an American did?
Yep, he actually taught at Columbia.
How come? Because we don't ever see, yeah, America's slacking.
Yeah, chemistry used to be controlled by the Germans, and now it's shifted to a lot of Americans and Japanese and Chinese chemists. So it's shifted from Europe westward or eastward, depending on your perspective of the world. All right, so let's think about this. If we treat cyclohexanone with LDA, we said that we would get a really, really unstable reactive enolate.
So if there was another double bond oxygen on there would be okay, right?
Yeah. Enolate, and in this case, won't do Michael addition. So his solution to this was, well, let's use chemistry we already know to get around this problem and make an enolate that's relatively stable. So he still started with cyclohexanone, but he treated it with catalytic acid and an amine, and he drove off water from this reaction. And if we have a secondary amine, what sort of product are we going to get out? An enamine, right? If we had a primary amine, then we would get an imine, but in this case, we're getting an enamine. So this goes back to the ketone chemistry that we've already covered. And the great thing with enamines is you have this resonance structure. So let me actually draw in the lone pairs. You have a lone pair on the nitrogen that can dump down. And when you do this, you have an alpha carbon that's now weakly nucleophilic. So in this case, this can act as a weak nucleophile. Oop. Oop. And in this case, it can do Michael addition. Which is pretty nice because we know eventually we can pop off our enamine and go back to the ketone by reacting it with water, right? So in this next step, what you can do is just react it directly with your alpha beta unsaturated aldehyde. And because it's a weak nucleophile, this enolate position will attack in the beta position. Kick down electrons and all the way up to oxygen. So we now have an aminium ion. And then, if we treat this with acid, what will happen to our enolate? So we've got an enolate over here. What happens to enolates when they're treated with acid? Yeah, they'll tautomerize back to their aldehyde, right? So if we look at the main structure of our molecule, that enolate over there will go back to the aldehyde. And then the other thing that we have is we've got our aminium. What happens to that if we treat it with acid? Yeah, it'll go back to a ketone. So we can, in one step, change both of these groups to their corresponding carbonyl, and you can get this Michael addition to work well. So it's a clever route, essentially forming an enolate that's relatively mild, do your Michael addition, and then deprotect it at the same time you're tautomerizing your enolate back to your aldehyde.
It's not that difficult.
It's what?
It's not that difficult.
It's starting to get difficult? Yeah. Thank you. All right, so let's do some practice. All right, let's figure out how to go from acetophenone
I don't think we know what it is.
You guys know what acetophenone
I know,
is.
I'm just playing, because the lab, you know.
You guys have a weird sense of humor. Even weirder than mine sometimes. All right, so let's do the synthesis for this molecule. We're going to be doing more synthesis tomorrow, so this is good practice.
Wait, we're doing what tomorrow?
Synthesis.
I think I'm sick.
You think you're sick? If you say the word fine, it has a D.
So the question I have for you guys before we even start, we have alpha protons here on the methyl group. If we deprotonate, is that going to be a stable enolate? Not really. It's not in between two carbonyl groups. It's not a common Michael donor. So what should we do in the first step?
Add that stuff.
Turn it into an enamine.
So H plus. And minus H2O.
Okay, this is an emo.
Are we doing this by ourselves?
Yep, work on it by yourself for a second and then we'll reconvene. All right, so I'll help you guys out with this enamine part.
So once it goes, once we move it, what is it?
All right, so we've got our enamine now. The question is, what other organic reagent do we need in order to get this to work? So if we look at our alpha position here, basically our whole new added group on here was this guy, right? So we need to come up with an alpha beta unsaturated ketone or aldehyde that would give us this product. So what I'll do is actually do this in a different color. So this electron can dump down. This one can attack here, oh, and attack up.
So like the key for that, when you add an orange 10 with a double bond or whatever, or should we attacking the double bond?
What's that?
I said for that, like you said that we need to have a saturated or whatever you said, but the key for that to have is just the attacking the double bond.
It needs to attack the beta position. So in this case, remember that we've got the alpha position here, and then over here we have our beta position. So it's going to attack the beta position of your alpha beta unsaturated ketone or aldehyde. All right, and then the last step is what? Acid. When we do this, we can get to our final product. which is our Michael addition product. So sometimes breaking it apart, trying to identify where your alpha position is, and then circling your substituents works pretty well. Do you guys want to see another practice with the
Sure.
Michael addition?
Yes, please.
All right.
Can I get some music?
Yeah.
Yes.
Something like really.
Background.
Do practice. Okay, this time we've got 3-pentanone as our starting material. And this is going to be multi-step, so I'll do a couple arrows. We want to synthesize this product. And you can use other organic reagents as necessary. I'll give you guys a hint too. It looks to me like our alpha position is right here, and our whole group that got added onto that alpha position was right there. So that alpha position I've shown in red is the same as that alpha position. So if we form an enolate, will it be very stable? So what do we need to do? Stork enamine. Let me clean this up. Okay, and then we need to identify what our alpha beta unsaturated ketone or aldehyde is.
I don't know how to say what I'm trying to say. So once I did that step, I thought you did the lone pair on the nitrogen down, so the bond would be in the middle, not where you have it.
So just like we had up here, we had an imine right here.
Yeah.
And then that lone pair will get dumped down and do an attack on the beta position.
So when you did resonance, before that,
So let's go back up and look at the resonance structure. Both resonance structures are perfectly fine. Obviously, the one on the left is going to be your major resonance structure because it's not charged. The one on the right is very minor. So you can draw it both ways if you'd like. But let's go back down and take a look at this. If we react this with an alpha beta unsaturated ketone, then this lone pair can jump down. This position can attack here, kick over, kick up electrons onto that oxygen. And then in the last step, we can just treat this with acid to get back to our ketone. So we're deprotecting our enamine essentially, or our aminium ion, and then tautomerizing our enol back to the ketone. So it's a pretty simple solution to what was a confounding problem for a long time. Michael additions are very, very popular in natural product chemistry. Some of you picked up the problem of the day already. That problem of the day is from a classic synthesis paper, and it's pretty challenging. So what I'm going to do is if you complete it, and you complete it correctly, it's 2 points extra credit going into your pod pool. If you don't want to complete it, it's fine, but I would encourage you to at least try.
Why not test?
All right, so let's continue on to a different type of reaction. The next reaction is called a Robinson annulation. And the Robinson annulation is an offshoot of Michael addition. It's a Michael addition. Followed by an whoa, shoot. I went too fast, I froze it. Come back. Ugh, shoot. Sorry. Ugh. Sorry guys, my computer's been glitchy today. It's followed by an intramolecular aldol condensation. Okay, so let's take a look at an example of the Robinson annulation. I think it's a pretty cool reaction, personally. So we're going to take this ketone and we're going to react it with sodium hydroxide. And we've got these really acidic alpha protons, right? So we can form a highly stabilized enolate and make our Michael donor. So now we've got our Michael donor. We need a Michael acceptor in order to do our Michael addition. So in this case, I'll use this as our Michael donor. And again, whoop, let me keep it red. This will attack our beta position, clamp down, and kick up electrons. And then the last part of our Michael addition is having this tautomerize back. Well, remember in the first step we used sodium hydroxide and made water. And this will quickly tautomerize back to our ketone. Okay, but now we've got sodium hydroxide around still. And so we've got some other alpha protons, and in this case it's a special group of alpha protons, and you'll see why here in a second.
There's a bunch of alpha. Why there's more than just that alpha proton?
Yeah, the reality is it can attack any of those alpha protons, and they're all in equilibrium. But in this case, bear with me for a second while I do this deprotonation.
Okay.
Trust me on this. It's pretty cool. Yeah, trust me, I'm a doctor.
Cold and mean.
All right, so now we've got our enolate.
More than what you're working with, Dr. Barry.
We've got 1, 2, 3, 4, 5, 6. Or actually, I'll do 6 down here. It doesn't really matter which position. So in this case, we can form a 6-membered ring. If we deprotonated the alpha protons on that 3 position, we wouldn't be able to form a stable ring. So in this case, the only alpha protons you can deprotonate and form a ring are the ones on that 1 position there. So this will come in, attack, kick up electrons. So let's see. I'm going to number this before we start adding substituents on. We've got 5 and 6 right here, and then 4, 3, 2, and 1. And so off of that 6th position, we've got our enol, or our alkoxide, I should say. Our 2 position, we still have our ketone. And then we've also got water floating around. So this alkoxide will quickly get protonated. And now we've got our alcohol. But with our aldol condensation, we said if you've got this alcohol around and you've got hydroxide, let me clean this up a smidge, that this base will come, grab here, clamp down, and kick off hydroxide.
What, how are we kicking off hydroxide? It doesn't need to be H3O plus. Like,
So hydroxide's normally not thought of as a leaving group,
right.
but in this case, what we are forming is a conjugated system, right?
Yeah, but how does it even come off? Like, because we were doing that in some previous problems.
So we're almost treating this like an E2 elimination, where we're just think of this as a generic leaving group. We've got a base grabbing a beta proton, clamping down, and kicking
But
off.
it's not a good leaving group.
So the only reason hydroxide is acting as a leaving group in this case is that by doing this, we create a highly stable conjugated
So that's
system.
more
So
important.
that's more important in this case. It's one of the weird examples of hydroxide acting as a leaving group. So in the Robinson annulation, you form these 6-membered rings. You may need to use this on your problem of the day a little bit. But one thing I wanted to point out on the problem of the day is, can you guys imagine being in the 60s and say, all right, this isn't even the final product, but say, all right, retrosynthetic analysis, what starting materials do I need to make this? And be like, oh yeah, obviously I need this guy. Like, this is the most elaborate game of chess you can play. And these guys that worked in the, guys and girls, I shouldn't say guys all the time, these scientists that worked back then, I mean, they were brilliant. They were doing chemistry that they had no right to be doing, but they just sheer willed their way into making these compounds. It's pretty incredible stuff. So I'll give you guys a day to work on this, and then tomorrow we'll do synthesis
Can
in
you go
class.
back to the notes, please?
Yep.
So we're going to have to come up with some crazy
Let me stop the recording really quick.
Yeah.